Welcome back, physics fans. Here we go on to graphing. This is a kinematics lesson of physics 11 in this case, but it's a one-dimensional kinematics graphing. Okay, a little bit of review to go first, a review for at least the students in the class at the moment. What is position? Position is in terms of its relationship to some other point. Using a scale, 0 would be our reference point. So we usually and almost always use our 0 as our reference point. It's position. So when you make 0 the reference point, you have chosen the reference frame. So basically when we start graphing and we have our graph with a 0 point, we have chosen our reference frame. Okay? The position of an object is the separation between that object and that reference point. Distance does not require a frame of reference. Distance is not important, it's scalar. Direction is not important, it is scalar. Okay? So we use plus or minus to describe that position. It is. How do we change our direction to plus or minus? How can we do that? Because I said we're in one dimension. We're in 1D. So we start graphing this. What information can you find on a DT graph? We can find a lot of information. In fact, I ask this question every time we start a new type of graph. What can we find on a DT graph? We can find position. Read the graph. That's what it's graphing position. So you can get the position all the time. Okay? We can also get the velocity. That's what we learned. Okay? The displacement is the vertical separation and the time is the horizontal separation. You don't understand what I just talked about? It's blah, blah, blah. The vertical is position and or distance if you want, d, and the horizontal is time. So if we take the slope, it's going to be the rise over the run, which is the displacement over the time, which is d over t, which is velocity. So I'm using the math of that if a equals b, then which equals c, which equals d, then a equals d. That's just type of commutative, I think they call it. So the slope is the velocity. Okay? The slope of a position time graph is velocity. So what I put into the oval, highlighted, that's what we just learned. Into the rounded rectangle. Displacement is determined by the height of the graph. Yeah, from a DT graph, we can read the graph, and that's how you get displacement. And velocity is the slope of the graph. Okay, end of review. Velocity time graphs. What information can we get of velocity? See, I told you every time we start a new graph, we ask, what can we get from that? Okay, and then once we learn all about it, then we kind of write it all down and put it in a nice rounded rectangle. What information can you get from a VT graph? Well, we can get the change in displacement and the acceleration, and also, guess what? From a velocity time graph, you can also find out what the velocity is. By reading the graph, you get information. But we can also get, I'm telling you now, where we're headed, we're also going to get what the change in displacement is, and we're also going to get the acceleration. So we basically get everything. We get the A, we get the VF, we get the VI, we get the D, and of course the base of it is time. So we get all 5 things from this graph. I love it. If the velocity is a vertical separation and the time is the horizontal, in other words, V is up here and T is this way, then the slope, which is rise over run, which is the velocity, and that's going to be the change in velocity going up, and this is the time, and the slope is the rise over run. So the slope is going to be the change in velocity over time. What is the change in velocity over time? That is the acceleration. So the slope of a VT graph is the acceleration. Dun, da, da, da. Okay, I might be just highlighting this and you're going, yeah, 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 but that's epic. Okay, if you have a highlighter, do it. If you have a pen, underline it. If you have a pencil, circle it. And if you have all three, then do all three. That's rule number 2. This is rule number 1. Okay, but this is the slope of a dt graph. The slope of a vt graph, velocity time graph, is acceleration. Okay, next page, here we go. From a velocity time graph, the change in displacement can also be calculated. There's 2 things we are learning from a velocity time graph today, besides just reading it. Okay, so here's a little bit of information. Displacement is velocity times time. And the area and the base is the velocity and the time. So I'm coming up here, here's our velocity, here's our time. That is the velocity and the time. And if I multiply that together, I am literally getting that area. If I take velocity times time, I get that area. That area is calculated by taking the height of it, which is our velocity, and the base of it, which is our time. But velocity times time, at least when you're staying at a constant speed, that's a constant speed, at least when you're changing it, is our displacement. So the displacement is the area under a velocity time graph. Okay? But that displacement is not saying where we started. If we see this graph, we don't know where we started. All we're seeing is that there's a velocity and you're moving. You have no idea where you are or where you're ending up. But what you're getting is the change in displacement. We're getting to see how much it changes. We don't know where it begins. That's what I just said. We don't know where it begins or where it ends, but we know it changes that much. And when I say the area under a graph, what happens if we have a velocity time graph that is like this, drawn from a big positive number and goes down to a small negative number? How do we get the area under that? A triangle, but we need to be a little bit careful than just a triangle. We want that triangle because we go to the 0 part and this triangle. And I'm going to do that one in purple. And this would be a positive area, and this would be a negative area. What would a negative area mean? Well, that means the negative area is the change in displacement, and it's negative. That means you're going backwards. Well, no, the velocity is negative. You'd be going backwards. We get a negative area, it means we're going backwards. So it's good. I love the no da. Okay, so here is our wicked large rounded rectangle learning. Velocity is determined by the height on a velocity time graph. Okay, so this is on a VT graph. Okay, sorry. I believe this whole rounded box is all about VT graphs. Velocity is basically read the graph, you got the velocity. Read the graph. Acceleration is the slope. And the change in displacement is calculating the area bounded by the velocity graph and the x-axis. Okay? I won't say it that clear much, but it is the area bounded by the velocity graph and the x-axis. That's what I just did there. I went to the x-axis, and it's the area underneath to the x-axis, area underneath to the x-axis. So those two yellow triangles I have to actually subtract, but I calculate those areas. It's not, this is what I get sometimes. I get, that's the area. It's not. It's not that. It's not to the bottom of my chart. It's to the zero. Okay, and the thing that I haven't talked much about and won't talk much about, but here it is. The average velocity during a time interval is defined as the net displacement divided by the total time. If I have a velocity time graph, how do I get the average velocity? Okay, well, it's a no-brainer, at least if it's not changing. If that's a velocity time graph, then that's the average velocity. But if the velocity time graph goes like that, how do you get the average velocity? We go back to chapter 1. What's the average velocity? Net displacement, total displacement over the total time. That's how you do it. Okay. I think I've done the notes there, but I wanted to talk about what happens, of course, if we have a line up here. I don't see the triangle. Okay? Literally, it's the area bounded by that red line. So there's my velocity time graph. I have to get the area of this. So how do I calculate the area of this? In Physics 11, we can do this. This is easy geometry 8. Grade 8. I'm sorry. So what we do is we look at it as a red triangle and a blue box, or at least a triangle and a box. I don't care what colors you call it. And to get that area, you get the area of a triangle, which is 1/2 base times height, and the area of the rectangle is base times height. Okay? The bases are the same. Okay? Can someone identify to me what this height is and what this height is? This is the height of the blue box. Okay? Which is this red line. What's the height of that red line? The height of that red line is that point, which is the initial velocity. If this is a velocity time graph, that's the velocity that we started at. So it just so happens that this is base, which is base times height, and the base is time, and the height is just the initial velocity. Okay? Is that good? That's like, ooh, I see that. Now I'm going to give you a few seconds to think about what is the height of that red triangle? What is the height of that red triangle? And I'm going to tell you right now, it's not the initial velocity, and it's not the final velocity. What is that height? That's right. The height of this, since this is the final velocity here, that black is the final velocity. This yellow height here is what we're trying to find out. That's the h here is the yellow height, and that is going to be the final velocity minus the initial velocity. And what is that? That is the change in velocity. Very good. That's the change in velocity. Anyone know what the change in velocity is in formula? Yeah, okay, it's VF minus VI. Another formula with acceleration in it? VF minus VI. Okay, how about this formula? VF equals VI plus AT. I take the VI to the other side. I get VF minus VI is equal to AT. Okay? That's AT. And the base is time. Okay? Please stay with me. This is going to be like, oh my gosh, you just did some magic in front of me. I'm going to do an illusionary trick right here, mathematical illusionary trick. Follow me. This is 1/2 time, and the height is, yeah, VF minus VI. That's how we'll do it 99% of the time. VF minus VI, and we'll do that. But I just told you that VF minus VI is AT. How about I put AT here? Let's just combine it, and I'm going to get 1/2 AT squared. You're seeing the magic. I'm saying that this displacement is the adding of those two, and that displacement is this blue box, which is VIT, plus the red box, which is 1/2 AT squared. Mind blown. Where do you think this formula comes from? This formula comes from the rule at a constant acceleration. I haven't said that much, but in chapter 2, that's what it's all about, constant acceleration. At a constant acceleration, the area under a velocity time graph is VIT plus 1/2 AT squared. I bet you never looked at this formula and said, oh, that's a box and that's a triangle. But that's what they were. So where did this formula come from? This law. So which is more important, this law or the formula? Of course, this law. And this is law number 3. I've told you 2 already. This one here is number 1. That's what we did in first chapter. And by the way, what formula came out of here? V equals D over T. The slope and what formula comes out of here? The slope of a velocity time graph. Velocity time graph. The slope is that, is the acceleration. Whoops, let's just not write it backwards for you guys to see it. So this formula came out of that law. This is the definition of acceleration. That's how we started the chapter, if you don't remember. And last but not least, this is law number 3. What formula comes out of there? This is one of the formulas. This is one of the formulas that come out of there. Is there another formula that comes out of there? Yes. Okay. Anyone know what the area of a trapezoid is? Why do I say that? This shape here is a trapezoid. This is a grade 8 term from math, right? You remember trapezoids? And the area of a trapezoid formula that you never had to memorize is 1/2 the sum of the two bases, or sum of the two heights. Base 1, no, height 1, sorry. Height 1 plus height 2, and you multiply it by the base. That's the area of a trapezoid. And that area is this red hashtag area, boom. And that is, by my claim of rule number 3, that's the displacement. Okay, but let's put V's and T's, because this is a velocity time graph in here. So I get D is equal to the sum of the two velocities V1 plus V2, I have to divide it by 2, and I have to multiply it by the base, which is time. Oh, I've just done another magic wizardry. I have done another magic wizardry. This is where that formula comes from. I bet you never looked at this formula and said, that's the area of a trapezoid, Mr. Curl. That formula is an area of a trapezoid. I could see it. I know. I've just done some magic wizardry. I see the smiles on your faces going, oh, okay, what other formulas there, Mr. Curl? What other formulas there? Sorry, not today. You don't get the VF squared equals VI squared plus 2AD. Not yet. But I bet you're looking at that going, what geometric shape is that? What geometric shape is that? Okay? So we're going to move on, and we're going to learn how to interpret this graph as an exercise. So we're going to work on it together. I'm going to let you go ahead and stuff like that. But what we're trying to do is read this velocity time graph, and the time is in seconds, and the velocity is in meters per second. And from this graph, we want to construct a displacement time graph and an acceleration time graph. So being given the velocity time graph, I want to know what this displacement time graph is going to look like. And I'm just sketching the acceleration time graph, but we'll know it exactly. Okay? Because the acceleration is very simple. Okay, so I'm going to give you time now. I'm going to stop this recording, send it up to the internet, and I love it. Start working on this if you can, and I'll plug in a few minutes and help you out. Thanks. Now subscribe, like, leave your comments down below. I'll return them. Replay it 18 times tonight. Fall asleep to it like you've been falling asleep in my class. Enjoy.